For billions of years, the sun has been our only source of life, a celestial furnace burning with the power of eternal nuclear fusion energy. But as our civilization grows, we face a critical turning point where traditional energy sources can no longer sustain our ever-increasing demand for power. Welcome to ITER, the most ambitious engineering project in human history located in southern France, where we attempt to build a star on Earth. This machine is a titan of technology, a structure so vast it rivals the world's greatest monuments in scale and complexity of its design. 35 nations have joined forces, putting aside politics to master the very laws of physics and secure a future of limitless clean energy for all. At its heart lies the tokamak, a revolutionary device designed to trap and harness the power of a miniature sun within its heavy metallic walls. Every layer of this machine is a masterpiece of precision, engineered to withstand conditions that would destroy any other material known to mankind today. Inside the chamber, isotopes of hydrogen are accelerated to incredible speeds, preparing for the violent collision that releases the core energy of the universe. To create fusion, we must turn gas into plasma, a fourth state of matter that flows like a river of fire trapped in a bottle. The engineering challenges are immense, requiring the assembly of millions of components with a level of accuracy thinner than a single human hair. Scientists from across the globe work tirelessly around the clock, pushing the boundaries of what is possible to achieve this scientific holy grail. Every movement of the plasma is calculated by supercomputers, ensuring that the magnetic cage remains perfectly stable during the intense heat of fusion. The fuel for this machine is found in seawater, meaning that a few gallons could potentially power an entire city for many generations to come. Deep in the heart of Provence, this quiet landscape hides the most powerful machine ever conceived, a beacon of hope for a sustainable future. Prepare to witness the dawn of a new era where humanity finally learns to control the fire of the stars right here on our home. The tokamak is often called an energy donut because of its unique shape, designed to keep the plasma circulating in a continuous loop forever. This vessel must be the emptiest place in the solar system, a perfect vacuum where particles can move freely without hitting any air molecules. Powerful magnets create an invisible cage, U-ending the path of the plasma so it never touches the walls, which would instantly melt under the heat. Maintaining this magnetic bottle is a deadly game of geometry, where even the slightest error could lead to a sudden collapse of the reaction. The scale of assembly is breathtaking, requiring thousands of experts to coordinate every bolt and wire with absolute perfection and extreme technical care. When the gas enters the chamber, microwave heating systems blast it with energy, stripping electrons from atoms and creating a roaring river of plasma. These cables carry massive amounts of electricity without resistance, providing the raw power needed to generate the strongest magnetic fields on the planet. Looking down into the heart of the project, one feels the weight of human ambition carved into the very earth of southern France's landscape. The magnetic field acts as a thermal barrier, keeping the core at millions of degrees while the surrounding equipment stays relatively cool and safe. Every inch of the plumbing and wiring is inspected by specialized robots, as the environment will eventually become too radioactive for human entry. Massive particle accelerators fire high-energy beams into the plasma, acting like a cosmic heater to push the temperature toward the ignition point of fusion. Plasma is notoriously unstable, behaving like a wild beast that must be constantly tamed and reshaped by the surrounding magnetic fields every microsecond. For the researchers, every pulse of the machine provides vital data, bringing us one step closer to a self-sustaining fusion reaction that lasts. These vertical coils are the pillars of the machine, standing several stories tall and weighing hundreds of tons each to support the internal pressure. Day and night, the work continues as the world waits for the moment the first plasma is sparked inside this technological marvel of engineering. The tokamak is more than a machine. It is a promise that we can harness the stars to light our way through the coming centuries. 150 million degrees Celsius. This is the target temperature, a heat so intense it defies the imagination of the human mind. That is 10 times hotter than the very center of the sun. On Earth, we must go hotter because our gravity is much weaker. At these extreme temperatures, matter enters the plasma state, where atoms are stripped bare and move with enough energy to overcome their repulsion. When they finally collide, they fuse, releasing a burst of energy that can be captured and converted into the electricity that powers our homes. Inside the vacuum chamber, it looks like a scene from hell, a raging inferno of energy contained by nothing but the power of magnets. Special materials like beryllium and tungsten are used to line the walls, acting as the ultimate heat shields against the brutal radiation of fusion. the heat must be managed perfectly. If the plasma touches the wall for even a fraction of a second, the reaction will instantly quench. Everything about this environment is extreme. It is a constant battle against the laws of thermodynamics to keep the heat inside the core. At 150 million degrees, any physical object on Earth would turn into gas in an instant if it made direct contact. The diverter at the bottom acts as the reactor's exhaust, taking the brunt of the heat and cleaning the plasma of any unwanted impurities. This is the most concentrated heat in the known universe, created by human hands within a machine made of steel, silver, and copper. Monitoring this artificial hell requires thousands of sensors, providing a real-time picture of the temperature distribution across every single millimeter of the vessel. Giant cooling loops circulate water at high speeds, carrying away the heat that will eventually be used to drive steam turbines for electricity. A disruption is the engineer's greatest fear, a sudden loss of control that sends the thermal energy crashing into the reactor's inner lining. Tungsten, the metal with the highest melting point, is our final line of defense against the relentless heat of the man-made sun's core. Walking into the hall during a test would be like walking into the heart of a star, a place where physics reaches its absolute limit. The fuel is simple, but the conditions required to ignite it are the most difficult challenge humanity has ever faced in its history. Once we master this heat, we will have a source of energy that is safe, carbon-free, and practically inexhaustible for all of time. Ignition is the goal. The moment when the fusion reaction becomes self-sustaining, generating more energy than it takes to start the fire. To control the plasma, we need the most powerful magnets ever built. Meet the central solenoid, the beating heart of the ITER reactor. This magnet is strong enough to lift an entire aircraft carrier. Its magnetic force is nearly 300,000 times stronger than Earth's field. These magnets create a complex gong or shackle of magnetism, ending the path of the charged plasma particles into a never-ending circle. Hundreds of miles of superconducting wire are wound into precise coils, each one designed to carry currents that would melt any normal wire. If a magnet is misaligned by even a single millimeter, the magnetic cage will leak, causing the plasma to crash and fail immediately. The 18 D-shaped coils are the pillars of the magnetic cage, standing 5 stories tall and working in perfect harmony to contain the sun. The forces involved are so great that the entire steel structure of the reactor would be ripped apart if not for massive support beams. Magnetism doesn't just hold the plasma, it compresses it, forcing the atoms closer together to increase the chances of a successful fusion event. Each magnet is a marvel of manufacturing, taking years to build and months to transport from factories located all across the entire world. To work, these magnets must be kept at a state of superconductivity, meaning they must be chilled to temperatures that are mind-bendingly cold. Once energized, the magnets hold enough stored energy to equal a massive explosion, requiring sophisticated safety systems to prevent a sudden release. The magnetic field is an invisible landscape, a perfectly crafted valley of force where the plasma can flow without ever finding an exit. Every bolt must withstand millions of pounds of force as the magnets try to push each other away with the strength of giants. The twist of the magnetic field is crucial. It prevents the particles from drifting toward the edges, keeping them locked in the center. Testing these systems is a delicate process, as the energy levels involved are far beyond anything ever handled in a laboratory setting before. The central solenoid is the conductor of this magnetic orchestra, pulsing electricity to drive the plasma current and keep the fire burning. Without these magnetic shackles, the project would be impossible. They are the invisible hands that hold the sun's power in our grasp. When you stand next to one of these magnets, you are standing next to one of the most powerful forces ever created on Earth. Together, they form a cage of light and force, a testament to human ingenuity and our desire to master the fundamental energy of nature. In the shadow of 150 million degrees, we must also create the coldest place in the universe. This is the world of the cryostat. The magnets only work at 4 Kelvin, just a few degrees above absolute zero. At this temperature, electrical resistance completely disappears from the wires. The cryostat is the largest stainless steel vacuum vessel ever built, acting as a giant thermos to protect the cold magnets from the heat. Liquid helium, the rarest of gases, is pumped through thousands of miles of channels, acting as the lifeblood that keeps the system frozen. Nowhere else in the cosmos can you find such an extreme temperature difference separated by only a few meters of advanced thermal insulation. Layers of silver-coated shields reflect heat back, ensuring that the warmth of the outside world never reaches the delicate superconducting core of the machine. ITER houses the world's largest cryogenic plant, a massive industrial complex dedicated solely to keeping the artificial sun's heart in a deep freeze. Without the vacuum of the cryostat, the magnets would boil instantly, causing a catastrophic failure of the entire magnetic containment system. In this realm of absolute cold, physics changes, materials become brittle, and electricity flows like water without losing a single watt of power. Operating the system is a high-stakes challenge, as managing the expansion and contraction of metals at these temperatures requires extraordinary mechanical precision. The entire 23,000-ton reactor sits on flexible supports designed to move as the machine shrinks and expands between the heat of fusion and cold. It is a cosmic irony. To produce the hottest fire in the galaxy, we must surround it with the coldest liquid on the planet. Superfluid helium behaves like no other substance, creeping up walls and flowing through the tiniest cracks to keep every corner of the magnet cold. Once the lid is closed, the reactor becomes an isolated world, a place where the extremes of the universe meet for the first time. The cool-down process takes months, a slow and careful descent into the deep freeze that will allow the magnets to finally come to life. This balance between fire and ice is the secret to fusion. It is the bridge between the stars and the future of human civilization. We have built a palace for the sun, a cathedral of steel where the most extreme conditions in nature are held in perfect frozen equilibrium. This is a global effort. Components for ITER are manufactured in every corner of the world, from the United States to China and Japan. 35 countries are sharing the cost and the knowledge, proving that when humanity faces a common challenge, we can work together as one. The logistics are a nightmare. Giant parts, weighing hundreds of tons, must be transported over narrow roads with only inches of clearance to spare. Despite their size, these parts are as delicate as a Swiss watch, requiring constant monitoring of vibrations and temperature during their long, difficult journeys. Assembly is a giant 3D puzzle. Each piece must fit perfectly with the next, or the entire machine will fail to function as intended. Engineers from India, Korea, Russia, and the EU work side by side, speaking a dozen languages but sharing a single common vision of the future. New technologies are being invented just to build ITER, from advanced robotics to new types of steel that can resist extreme radiation for decades. A digital twin allows engineers to test every step of the assembly in a virtual world before a single piece is moved in reality. The craftsmanship is unparalleled. Some parts require months of hand polishing to ensure they meet the rigorous standards needed for high-energy physics experiments. This is more than a construction site. It is a global village, a place where the brightest minds of our generation gather to solve energy. Month after month, the pieces arrive, bringing with them the hopes of billions of people who dream of a world without pollution or war. The precision is so high that sections weighing 400 tons must be aligned within a fraction of a millimeter to ensure a perfect vacuum seal. Every person here knows they are part of history, building a legacy that will last for centuries and change the course of human development. ITER is the proof that when we work together, no challenge is too big and no law of physics is beyond our collective human reach. The construction of ITER is the ultimate relay race, a global marathon where each nation passes the baton to the next for one goal. One by one, the systems are coming online, bringing the world's most complex machine closer to its first historic spark of life-giving energy. Imagine a world where energy is as free as the air we breathe, a world without carbon, without waste, and without limits to growth. The fuel for a fusion future is hidden in plain sight. In a single glass of water, there is enough energy for a lifetime. This is the promise of ITER, a clean planet for our children where technology and nature finally live in a perfect, sustainable balance together. Fusion is the missing piece of the puzzle, the steady power source that can back up our wind and solar systems for an eternity. Once ITER proves it can be done, the next step is demo, the first power plant that will actually put fusion electricity onto the global grid. Fusion will not just save our world, it will help us explore others, providing the massive power needed to travel across the stars themselves. We are standing on the threshold of a new era, the era of the artificial sun, where humanity finally controls the source of all life. The sun is rising, not in the sky, but here on Earth, in a machine built by the hands of 35 united and brave nations. The journey has been long and the challenges are great, but the prize is nothing less than the survival and prosperity of our entire race. ITER is our gift to the future. A star on Earth, a light for humanity, and the ultimate victory of science over the impossible. The age of fusion has begun. Let there be light for us, for our children, and for all the generations that are yet to come.